On January 5th, 2024, an Alaskan Airlines Boeing 737 MAX 9 took off from Portland, Oregon. Just minutes into the flight, a door plug panel blew out of the side of the aircraft, leaving a gaping hole in the cabin. Fortunately, no one was killed, and the plane landed safely. The images were everywhere. Passengers shared videos and photographs from inside the plane. News outlets replayed the footage for days. Social media was filled with comments from people saying they were suddenly nervous about flying, that they would avoid Boeing aircraft, or that they were reconsidering upcoming trips. Airlines received questions from concerned passengers. The FAA grounded dozens of Boeing 737 MAX 9 aircraft, while investigators tried to determine what had happened. At the same time, aviation experts pointed out that commercial air travel remained extraordinarily safe. They noted that millions of people fly every day and that serious accidents are exceedingly rare. Then came a flood of numbers. How often do incidents like this happen? Have they become more common? Has the risk of flying increased, and if so, by how much? These sound like straightforward questions, but answering them turns out to be surprisingly difficult. A single dramatic event can feel like powerful evidence. A reassuring statistic can sound conclusive, yet neither tells the whole story. To make sense of what happened and to decide whether anything about our behavior should change, we need to understand what these numbers actually mean. Why did Alaska Airlines incident have such a powerful effect on so many people? Part of the answer lies in how we think about uncertainty. As human beings, we're often forced to make decisions without having all the information we would like. Is something dangerous? Is this person trustworthy? Should I be worried about what just happened? For most of our history, there were no spreadsheets, no risk calculators, and no statistical models to help answer questions like these. Instead, we had to rely on experience, pattern recognition, and quick judgments based on limited information. As a result, the human mind became very good at spotting unusual events, recognizing patterns, and drawing conclusions from incomplete evidence. Most of the time, that's incredibly useful. But many modern decisions ask us to do something different. How much has the risk changed? How common is this event? What is the probability that this outcome will occur? Questions like these often require us to slow down and think more carefully about the evidence. Psychologist and Nobel laureate Daniel Kahneman described two broad modes of thinking that people use when making judgments and decisions. System one is fast, intuitive, and automatic. It's what gives us our immediate impressions and our gut reactions. System two is slower and more deliberate. It's the system we use when we pause, question our first impressions, and work through a problem more carefully. Most of the time, these systems work together remarkably well. But when we're reasoning about risk and uncertainty, our first intuitions can sometimes be misleading. A dramatic event can make a risk feel much larger than it really is. A statistic can sound alarming even when the actual change in risk is quite small. And probabilities that seem straightforward can turn out to be surprisingly difficult to interpret. Understanding risk, therefore, often requires us to engage system two, to slow down, examine the evidence, and ask, what do these numbers actually mean? One of the first things we learn when thinking about risk is that percentages can be surprisingly misleading. Suppose you read the following headline: A new treatment cuts the risk of heart attack by 50%. That sounds enormous. A 50% reduction in risk seems like exactly the kind of result that should change people's behavior. But before drawing that conclusion, we need to ask 50% of what? Suppose that without the treatment, 2 out of every 10,000 people experience a heart attack. Now suppose that with the treatment, 1 out of every 10,000 people experiences a heart attack. The treatment did reduce the risk by 50%, but in absolute terms, the reduction was only 1 fewer heart attack per 10,000 people. Those are 2 very different ways of describing exactly the same result. The first is called relative risk. It tells us how much the risk changed compared to where it started. The second is called an absolute risk. It tells us how much the risk actually changed. Psychologist and risk researcher Gerd Gigerenzer has shown that people often misunderstand risk information when it's presented only in relative terms. In fact, this misunderstanding is common even among physicians and other health professionals. And it's easy to see why. A 50% reduction sounds dramatic. 1 fewer case in 10,000 feels very different. Neither statistic is wrong, but without both pieces of information, it's difficult to judge how important a finding really is. Of course, understanding what a statistic means often requires more than the statistic itself. We also need to know something about the broader context in which the event occurs. One important piece of that context is the base rate, the background frequency or prevalence of an event. Consider the following statement. An eyewitness correctly identifies the suspect 80% of the time. That sounds persuasive. But is it enough information to decide whether the eyewitness is probably correct? Not quite. To answer that question, we need more than the eyewitness's accuracy. We also need to know something about the situation. Was this one suspect among several likely candidates? Or was this one person identified out of thousands of possibilities? Questions like these require us to consider the base rate. In other words, before the eyewitness said anything, how likely was it that this person was actually the culprit? Daniel Kahneman and Amos Tversky found that people often pay too little attention to base rates when making judgments under uncertainty. Instead, we tend to focus on information about the specific case in front of us. An eyewitness account can be compelling. A personal story can be compelling. A dramatic example can be compelling. But focusing on those details, we sometimes overlook the broader statistical information. Kahneman and Tversky referred to this tendency as base rate neglect. Base rate neglect appears in many different situations. People often overestimate their chances of winning the lottery because they can easily think of someone who won. They overestimate the likelihood that a new business will succeed because they can think of successful entrepreneurs. They overestimate the chances that a young athlete will become a professional player because the exceptional success stories receive so much attention. In each of these cases, the underlying statistics are easy to overlook. Yet those statistics often provide some of the most useful information we have when making predictions and judgments under uncertainty. Base rates tell us how common an event is. Often, however, We want to answer a different kind of question. We want to know the probability of one event after learning that something else has happened. Psychologists and statisticians refer to these as conditional probabilities. A conditional probability is simply the probability of one event given that another event has occurred. Consider a positive medical test result. Most people want to know the probability that they actually have the disease. Before the test, all we know is the base rate, how common the disease is in the population. Once the test result is available, however, we're going to be asking a different question. What is the probability that this person has this disease given that they tested positive? This is a conditional probability. Importantly, this is not the same thing as asking how often people with the disease receive a positive test result. These two probabilities are easy to confuse because they sound similar, but they answer different questions. Research by Gerd Gigerenzer and his colleagues has shown that people, including physicians and other highly trained professionals, often struggle with this type of reasoning. Part of the difficulty is that abstract possibilities can be surprisingly hard to reason about, even when they're expressed as percentages. Fortunately, there's a simple way to make problems like this easier to understand. Instead of expressing the information as abstract probabilities, we can express it as natural frequencies. Imagine an airport security system designed to identify potentially dangerous passengers. We know the system won't be 100% accurate. To be able to determine how good this system is, we might want to know whether someone who is flagged by the system is more likely to be dangerous or innocent. Notice that this is a conditional probability. A statistician might even phrase the question as, what is the probability that a passenger is genuinely dangerous given that they were flagged by the system? Suppose the system correctly identifies a dangerous passenger 90% of the time and incorrectly flags an innocent passenger 1% of the time. The base rate of genuinely dangerous passengers, however, is only 0.001%, 1,000%. These percentages sound informative, but they can be difficult to interpret. So let's translate them into natural frequencies. Suppose 1 million passengers pass through the airport. A base rate of 0.001% means that only 10 of those passengers pose a genuine threat. That leaves 999,990 passengers who are not dangerous. Next, let's consider the system's accuracy. If the system correctly identifies dangerous passengers 90% of the time, then it will flag 9 of the 10 dangerous passengers. Now consider the false positive rate. If the system incorrectly flags innocent passengers 1% of the time, then it will also flag about 10,000 of the 999,990 innocent passengers. At this point, we have all the information we need. Among the passengers who are flagged by the system, 9 are genuinely dangerous. About 10,000 are innocent passengers who were flagged by mistake. Now we can answer our original question. What's the probability that a passenger is genuinely dangerous, given that they were flagged by the system? Because only 9 out of approximately 10,009 flagged passengers are actually dangerous, the answer is about 1 chance in 1,100. Because we express the information as natural frequencies, the answer is now much easier to see. Now, at first, that result may seem surprising. The system is highly accurate, yet a positive result provides very little evidence that a particular passenger is dangerous. The reason is that genuinely dangerous passengers in this situation are extraordinarily rare. This low base rate overwhelms the accuracy of the screening system. Research has consistently shown that presenting information in this way using natural frequencies makes conditional probabilities problems easier to understand and often leads to better judgments, both by novices and by experts. Now, at first glance, concepts such as relative risk, base rates, and conditional probabilities might seem highly specialized. In reality, they arise whenever we have to make decisions under uncertainty. We encounter these ideas when interpreting medical information, evaluating financial risks, assessing news reports, considering public policy, and making predictions about future events. In each of these situations, the quality of our judgments depends in part on how accurately we interpret numerical information. Research in judgment and decision making has repeatedly shown that people often struggle with these tasks. We tend to focus on vivid examples, overlook base rates, and misinterpret probabilities. As a result, our intuitive judgments can sometimes differ substantially from what the evidence suggests. Learning to think statistically does not eliminate uncertainty, nor does it guarantee perfect decisions. It does, however, provide tools that can help us reason more effectively in situations where outcomes are uncertain. The concepts we have discussed in this video suggest several useful questions to ask when evaluating information about risk and probability. Is this statistic describing a relative risk or an absolute risk? How common is the event being described? What's the relevant base rate? Would the information be easier to understand if it were expressed as natural frequencies rather than as percentages or probabilities? These questions don't require advanced mathematics. Instead, they encourage us to examine numerical information more carefully and to consider how different ways of representing information can influence our judgments. The broader lesson is that intuition and data each have important roles to play in decision making. Intuition is often useful when we have extensive experience and receive clear feedback about our judgments. In situations involving probabilities, rare events, and statistical relationships, however, intuition can be misleading. In these situations, careful attention to data and evidence can lead to better informed decisions.